Alright, so far we talked about GIS data, including the spatial and attribute components. We learned how to organize attributes in a database and how to represent a spatial component with coordinates. From today's class, we start learning how to produce GIS data from scratch. First, let's look at major sources of GIS data sets. Keep in mind that GIS data collection and production is the most expensive and time-consuming task in a GIS-based project. There are a variety of GIS data sources out there, such as existing databases. For example, you can download the shapefile or spreadsheets from websites such as USGS, NASA, US Census Bureau, CDC Wonder, which are actually computer databases. The second source of GIS data sets are satellite images and also air photos. Information such as vegetation cover, air pollution, land cover type, land surface temperature can be obtained from satellite images. Also, you can acquire GIS data directly from GPS device and land survey. And historical and hard copy maps are other sources of GIS dataset. So today we're going to talk about GPS, which is an important source of GIS data, and in the following weeks we will talk about hard copy maps. So in today's class, first we'll start with GPS history and its component, and then principle of GPS, and finally possible errors in GPS. So what is GPS? First, let's talk about its general term that also covers GPS, which is GNSS. The GNSS stands for Global Navigation Satellite System. It refers to using satellite system to provide accurate locations across the world. GNSS is one of the most widely used techniques to collect field data for GIS. The most important GNSS is called US NAVSTAR, or Navigation Satellite Timing and Ranging, which is the GPS we actually refer to. The second GNSS is Russian GLONASS, which stands for Global Navigation Satellite System. The next GNSS, which recently completed, is Galileo by European Union, and finally the COMPASS Satellite Navigation System by China, and is expected to be completed by 2020. So these are GNSS, which means using satellite system that can provide accurate locations for positioning. So GPS is part of GNSS, and GNSS includes GPS, Galileo, GLONASS, and COMPASS. So let's talk about the history of US NAVSTAR, or GPS, first. GPS is a system with 24 satellites, so these are satellites that orbit around the Earth. The first satellite was launched in 1978, and the operational test for the whole GPS system was actually during the Gulf War in 1990, and the entire system or constellation was completed in 1995. In the year 2000, 3 satellites were turned off by the order of President Clinton. Now we have 21 satellites active and 3 as spares. So that's the general history of US NAVSTAR, or GPS. The second GNSS is Russian version, the GLONASS, which stands for Global Navigation Satellite System. It was launched almost at the same time as the US GPS, so there were competition between US and Russia. And GLONASS developed by Russian Federation Ministry of Defense in 1978, and also the project was completed in 1995, almost the same time as GPS. So like GPS, it is also composed of 24 satellites orbiting around the Earth, 21 active and 3 as spares. The next GNSS is Galileo system, which is supported by European countries, especially Germany and Italy, and also 6 non-European countries, including China, India, and Israel. The first satellite was launched in the year 2005 in Kazakhstan. This system is composed of 30 satellites, so number of satellites compared to GLONASS and NAVSTAR is higher. It's 27 active and 3 as spares. And the project is recently almost completed. The purpose of this project is to provide better accuracy in high northern latitude than US NAVSTAR, and I think the accuracy is less than 20 centimeter. In this lecture, we will only focus on US GPS, so let's talk about the components of the GPS system. So as you know, any system is a collection of linked components that work together for a specific purpose. GPS also is a system, and it has three components: a space component, control component, and user component, and the purpose is to provide accurate coordinate or positioning for location. So let's talk about each component of GPS one by one. A space component refers to the satellites. The system is composed of 24 satellites, and they are orbiting around the Earth at an altitude of almost 20,000 kilometers or 12,500 miles above the Earth's surface. So it takes 12 hours for each satellite to orbit the Earth, so every day they orbit the Earth twice. And the satellites are solar powered. They also are equipped with backup batteries and a rocket booster to adjust their orbits. Each satellite costs $25 million, and they weigh 2,000 kilograms or 4,400 pounds. The key part of space segment is the hydrogen atomic clock. What is atomic clock? This clock is very accurate clock. It only loses 1 second for every 2.7 million years. Simply, GPS satellites are nothing more than a set of clocks flying in space. That's the space segment, satellites which carry atomic clocks. The second component of GPS is the control segment. The main functions of control segments: first is to track satellites and to make sure satellites are working properly, or if necessary to adjust orbit or clock. The second function is time synchronization, basically to sync the satellite time and Earth time, and also upload navigation messages to control navigation of satellites. And this is a map of GPS control stations. There are a number of GPS control stations distributed across the world to maintain the satellites. And master control station here is located in Falcon Air Force Station near Colorado Springs, this red star. The last segment of GPS is us, users, who use GPS service. There are two types of GPS users: military and civilian or non-military. Military users need secure channel and have access to very high accuracy in positioning. And the other type is civilian, who have access to open data with a reasonable accuracy, for example, for navigation with car. These were the three components of GPS: space segment, control segment, and user component. Now let's talk about working principles of GPS. So in this module, we want to see how satellites work together to help us to determine coordinates of location or positioning. So GPS positioning is based on a range distance between the receiver here and the satellite. Okay, so we need to calculate the distance between our receiver and satellite. How this distance can be calculated? Theoretically, it's very simple. The range distance between a satellite and receiver equals to the speed of signal times travel time from satellite to receiver. The speed of signal is actually a speed of light and is a constant value, an already known value. The question is how we can calculate travel time between satellite and receiver. So if we have this information, if you have the time information, we plug them into this formula, and then we can have the range distance, and the problem is solved. Okay, so how this works: the satellites broadcast signals with time information. So basically, the satellites send out a message about the time that this message was sent. So we have the time of sent recorded in the message, and then this message is received by the receiver, okay, after a while. So when your receiver gets this information, this message, it will record the time of receipt. So GPS receiver decodes the message sent from the satellite, so it will know the time of sent. So now we have two times: the time of receipt and the time of sent. Okay, so if we do the difference between time of receipt, which is T1, and time of send, which is T0, so we have the duration, right? So we have the traveling time of the signal from satellite to the GPS receiver, and c is the speed of light, which is known, so we can have the range distance. So now everything is known. Plug them into the formula: speed of light times travel distance, so you will have the range distance between the satellite and the GPS receiver. So now, based on range distance, let's talk about how GPS helps us to determine the location. With the knowledge of range distance from only one satellite, the receiver must be on a sphere which is centered on the satellite with the radius equals to the range distance. So if we know the distance, let's say the distance is r, okay? Any location, and here there's a satellite, any location on this satellite, on this sphere, has the distance of r, okay? So the problem is there are unlimited location on the sphere, so that's why we need the help from another satellite, okay? By knowing the distance to receiver of the second satellite, like R2, so let's say this one was R1, this one was R2, we can draw another sphere center on the second satellite and the radius of R2. Now the receiver must be on the intersection between these two spheres, and the intersection gives us a circle. So this shaded area is actually the intersection of two spheres, which is a circle. But again, there are unlimited locations on this shaded area. That's why we need a third satellite, okay? So again, knowing the distance of the third satellite, let's say this one is R1, this one is R2, this one is R3. So we draw the third sphere, and then GPS receiver or your location must be on the intersection of these three spheres, which gives us only 2 points, this one and this one. But still there is ambiguity, okay? So this is the 3 satellites is still not enough. We want a unique location. That's why we need 4 satellites, okay? So the receiver, when we have 4 satellites, when our receiver can have access to 4 satellites, the intersection of the 4 satellites gives us only one unique location, which is here. So that's where your receiver is. That's the location of your receiver. So remember, any GPS receiver has to connect to 4 or more satellites to help us to determine the location. And the more satellites you connect to, the better accuracy you can achieve. That's the working principle of GPS. So if someone asks you for positioning using GPS, how many satellites your receiver needs to be connected, your receiver needs to be connected to at least 4 satellites for positioning by GPS. So now let's move on to GPS signals. As we talked about just now, the entire positioning process in GNSS, like GPS, Galileo, Compass, and GLONASS, is totally based on the signals sent from each satellite. And the signals are generated by the atomic clock, and they contain information about time. So the GPS signals contain 3 plus 2 types of code. Let's talk about the 3 codes first. The 3 codes are meaningful codes, which means that they can be understood by us. The first code is navigation message, which contains the position of satellite in space and also the time of sent. So the second one is CA code, or course acquisition code, which is a range code to help us to measure the distance from satellite to receiver. Coarse means the accuracy is low, and this code is available for civilian use. The third code is P code, or precise or private code, which is another ranging code but is much more accurate than CA code and can be accessed only for military purposes. So these 3 codes, CA, P, and message codes, are meaningful but have very low frequency. Low frequency means they cannot travel a long distance in space and they will decay in space. So that's why we need plus 2 codes. So the other 2 codes are called carriers, and they are vehicles that carry these 3 codes from satellite to the earth. So think about 2 very high speed vehicles like jets that their responsibility is to carry CAP and message codes. So these two carrier signals called L1 and L2 are used to carry information, are used to carry CAP and message code, but themselves don't carry meaningful information. So they are in high frequency or high energy, which means they can travel a long distance from satellite to the Earth's ground, and the L1 carrier is used to carry CA and P, but L2 carrier only carries the P code. So let's see how GPS signals are sent. The three codes with information, CAP and message, are modulated onto the carrier, and they are transmitted back to the Earth's surface. And then our GPS receiver receives these codes and demodulate and decode the signals to obtain useful information, such as where satellite was, what was the time of send, and what was the time of receipt. And then we can calculate the range distance, draw spheres, and finally determine the exact location of the receivers. That's how GPS works. Depending on which code you are using, there are two types of services. A standard positioning service, that's for daily use, such as car navigation. And for a standard positioning, GPS receiver is usually configured with quartz clock, which is much less accurate than atomic clock, such as a car GPS or cell phone GPS, all use a quartz clock. And we use the CA code ranging, which is a quartz acquisition code, and it's less accurate and is used for civilian use. The second type of service is precise positioning service, which uses the P code, precise and private code, and it has two frequency channels because this code is carried by both L1 and L2 carrier, so they can use two channels to do the comparison and make corrections. And this commonly used for national interests such as military purposes. So depending on which signals being used, there are different types of GPS receivers and also different prices. For example, for recreational purposes of daily use, the accuracy is low, almost 25 feet, and the price also low, between 100 to 600 bucks. It could be even cheaper by now. You can buy it from internet, and they are very user friendly. For mapping purposes, you need higher accuracy GPS, almost 3 feet accuracy, and the price is higher, from 1,000 to 3,000, and this is used by government agencies. And for geodetic survey, which is a very accurate process and considers even the Earth's curvature, we need much more accurate GPS receivers, like with the accuracy of few inches, and the price goes above $8,000, $9,000. So the more price you pay, the better GPS you will have and the better accuracy you will get. So let's move on to the last module. So far we learned working with principles of theoretically the design is perfect, but in practice there are always issues that cause error. In this module, we will review the sources of GPS errors. Let's first talk about the simple scenario which only concerns with a single GPS satellite. So the design of GPS is perfect, but errors are unavoidable in practice. The problem is we cannot measure the range distance accurately. Why? Because all of these items, speed of light, time of send, and time of receipt, are not as simple as we thought. There are always errors in all of these parameters. Okay, so first let's look at the speed of light, or the traveling speed of signal. We think that speed of light is a constant value, 300,000 kilometers per second or 186,000 miles per second, but it is not true in reality. The physics says the speed of light is only constant while passing a uniform electromagnetic field and in vacuum. But in reality, the Earth is surrounded by a blanket of charged particle, which is called ionosphere. The density of particles in ionosphere is not uniform and changes over time and space, resulting in dynamic electromagnetic field surrounding Earth as opposed to uniform. So the electromagnetic field is not uniform as we assume. That's why we can see aura in the polar areas. Fortunately, there are several physical models to reduce this error. Also, below the ionosphere is troposphere, and there are charged particles in the atmosphere, so it is not a vacuum. Its density changes in the temperature, air pressure, and humidity. So again, it's not a vacuum, and traveling speed of light is not constant because atmosphere is too complicated. But so far there are no good models for correcting atmosphere effects because it's very difficult and it changes every single second. So now let's go to the second item in this formula, which is T0, or the time of sent, the time signal was sent from the satellite. Atomic clocks from satellite may be unsynchronized as compared to the Earth's time, or it is malfunctioned. But typically this is the smallest error that may occur in GPS measurements. But remember that we have selective availability, which means that government can introduce artificial errors into the satellite because they have control over the satellites and atomic clock. So they can artificially introduce errors to reduce the GPS positioning accuracy. The purpose is to discourage hostile forces from using GPS, especially during wars. And it might be the largest source of error, but they are correctable. It adds a large error to the location, and only military has the correction information. But for civilian, there is no way to correct the errors. So that's the error from the satellite side. Now let's look at the T1, the time of receipt. That's the error from our side, from our GPS receiver. The GPS receiver have much less accurate clock, which is quartz clock, as compared to the atomic clock on satellite. For example, if our handheld GPS has timing error for only about 1/1,000,000 seconds, this formula will give you about 300 meters error, or almost 1,000 feet error in the location. So that's a lot offset in the position. In addition, there is another type of error called multi-pass error. What is that? Ideally, the signals sent from satellites are supposed to reach the receiver directly. So that's how we actually apply this equation. But in practice, the signals might be reflected by ground, might be reflected by the mountains, might be reflected by the trees. So this reflected multipath signal travels longer distance than the direct signals and introduces offset in position. So remember, we assume the signals traveling in a straight line, but actually the signals might be reflected by many times until it reaches the GPS receiver. That's called multi-path error. So this is often a problem in urban settings, or if you are navigating in mountain areas. That's why when you collect data with GPS, you have to stay away from the tall buildings or trees. So these were possible errors only from a single range measurements from just one satellite. And we know the GPS positioning is based on multiple satellite signals. Let's see the error from multiple satellites. Error from multiple satellites is much more complicated issue. So let's say this satellite produces uncertainty in the distance. So, and then we draw a band rather than a circle. So it's not just one circle, it's going to be a circle between this one and also this one because of the range uncertainty. Okay, so we will have a band rather than one circle. So if we add the second satellite, okay, so like this, again, it creates a band rather than one circle because of the uncertainty. So now if we add the third one, again, a band, now the intersection of all of these bands from all of these satellites is going to be this shaded area. Okay, so intersection is not, so if we add also the fourth satellite, the intersection is not going to be just one location. The intersection is going to be an area because of the uncertainty. And receiver can be any location within this shaded area. Okay, so that's the GPS error from more than one satellite. And also, geometry of satellite constellation is another important factor that affects the positional accuracy. So here, the first figure on top, these two, shows that we have two separate satellites, these two satellites, okay, that are in a decent distance of each other, and the intersection between them is this small area, right? This small area. While when two satellites are close to each other, so this one and this one are very close to each other, we can see that the intersection between these two is a ring, which is here, which is a larger area. So when satellites are closer to each other, you will have higher uncertainty in measurements than the two satellites that are distant in a decent distance from each other. So it is important how far or close satellites are from each other in a space.